All right, good morning everybody and welcome to this Let's Talk Meshing webinar. In this webinar, we're going to be talking about meshing considerations for automotive design optimization. Joined with us today is Mark Landon. Mark is the Chief Technology Officer and founder of Optimal Solutions Software and the architect of Sculptor, a tool which is used for morphing and shape optimization. Mark received his PhD in structural mechanics from BYU in 1989 and has been a mechanical engineering adjunct professor at a number of universities, as well as a senior advisory engineer at the Idaho National Labs. So thank you for joining us, Mark. My name is Travis Kerrigan. I'm a senior engineer here with Pointwise, and what I do is I work with clients to help strengthen their CFD process by developing interactive solutions using our Pointwise grid generation software and automated meshing solutions using our Glyph scripting language. So today we're going to be talking about optimization and how to prepare grids for optimization. This is the typical optimization workflow where you generate CAD in a CAD package and you parameterize it. You then pass that on to a mesher. You generate your mesh, you pass it on to a solver, which will compute your objective function value, and then pass it on to an optimizer, which would suggest changes to the parameters that would regenerate the geometry. Then you go and regenerate the mesh and then resolve. And you go through this loop over and over again for each new design. The problem with this is that sometimes it is very challenging to parameterize CAD, particularly if it is very complex. Not to mention, if you parameterize CAD and you regenerate that geometry and pass it on to the mesher, you have to remesh it for each design, which can be very time consuming, not only from the standpoint of automating that process, but also just from generating the grid in general, hundreds or thousands of times throughout the optimization. The other thing to keep in mind is that you now no longer can guarantee that the changes in the solution and the objective function value are coming from the changes in the parameters for the CAD, or if they're coming from the changes to the mesh, okay? Because we know that the mesh is going to influence the solution, and if we have to remesh each design, it's going to change for each design. So what we propose and what a lot of people are doing is they're decoupling CAD and meshing from this optimization process. They're generating CAD up front, they're creating very high quality grids, and then they're passing that into an optimization routine which will actually perform morphing of that geometry, of that mesh. So it's the exact same mesh, but they're morphing it and then running that through the solver and the optimizer to get the results. And they're able to do this hundreds or thousands of times with a single mesh. So the tools that we use for this are Pointwise to generate the mesh, and that's what we're going to be talking about in the first half of this presentation, and then Sculptor to perform the shape deformation and optimization, and then OpenFOAM to actually run the calculation and compute the objective function value that we're looking for. So I'm going to be talking about how Pointwise was used in this study, which is the study for the DrivAer, and then Mark's going to talk about how Sculptor was used. So the model that we used for this study was the DrivAer. It's a model proposed by the Institute of Aerodynamics and Fluid Mechanics at the Technische Universität of Munich. It's a realistic external automotive geometry that was developed in cooperation with both Audi and BMW. And you can see that there are a lot of parts here. You got the body, the underbody, the wheels, mirrors, and the back. And you can choose from one of three different backs. And we chose the fast back, the one in green. And there's experimental data that's available for us to compare against. Okay, so this geometry is complex. Complex from the standpoint that there's a lot of surfaces that exist, okay? It's actually a very smooth, aerodynamically smooth geometry. So it's simple in that respect, but it's complex, again, from the standpoint there are 15,000 surfaces when we imported this into Pointwise. And that's a lot of data to deal with, okay? But through solid modeling in Pointwise and solid meshing, we're able to distill that down to about 7 models. A watertight model that represents the body of the car, the mirrors, the wheels, okay? Those watertight regions we're able to mesh, and that mesh is guaranteed to be watertight. And again, that's referred to as solid modeling and solid meshing. One more part in that process is called quilting. And what quilting does is it allows you to simplify the topology of those surfaces. and create these nice logical meshing regions that you could create boundary conditions for downstream. So we were able to take 15,000 unique surfaces and represent those with 400 quilts. It's actually the exact same geometry. Those quilts contain all the information regarding the underlying trim surfaces and their UV parameterization. So we're still meshing on the same geometry, but effectively we're able to simplify the complexity of that surface mesh, because each one of these quilts is going to get its own surface mesh or domain in Pointwise terminology. So what I'd like to do is actually show you what that looks like. Now this process, I've actually recorded it because this process takes about 30 minutes. Okay, so I actually did this for the body and the back. I created the solid model, I quilted it up, and I surface meshed it, and I recorded the whole process. It was about 27 minutes, and so I sped it up and recorded it, and I'm playing it here, and I figured I'd talk through that process. Now, I do realize that playing a video online through a webinar may be a little choppy, and I'm hoping that it turns out well. If it doesn't, there is going to be a recording of this webinar available for you to watch as early as Friday, and I encourage you to go and watch this part of the webinar if it does happen to be significantly choppy. But I'm hoping that you get the basic idea of solid modeling from this video. So basically what's going on is I've imported the body of the car, and I'm creating a solid model for the body, and then I'm organizing it. I'm tucking it in its own layer. And then I'm basically going to do the exact same thing for the back. So you could imagine doing this for each component of the geometry. So I'm reading in the fastback. Okay, there's the fastback. And I'm going to create a solid model for the fastback. Okay, and now I'm just going to inspect it to see if there are any issues on the surface, any lamina boundaries. A lamina boundary is a free edge, and I've identified this little spherical surface that was used in the construction of that fillet. So I'm just going to delete that. I don't need it. And in doing so, it pokes a hole in that geometry, which is fine because I can grab those boundaries and I can create a Kuhn's patch to kind of fill that hole and then add it back to the model definition. Okay, so this demonstrates how you can use various tools in Pointwise to clean up and heal your geometry. Okay, so now I have a watertight representation for the fastback, and I'm tucking it in its own layer, again, organizing the geometry. And then I'm turning both layers on, and what I'm going to do is I'm going to stitch these two models together to create a single watertight model representing this vehicle. Okay, and the one thing to note here is I have 0 lamina boundaries. Again, a lamina boundary is a free edge. That's a gap or a hole in the surface. And in this case, I have 0 lamina boundaries. That means that this geometry is watertight. If I were to mesh it, I would have a watertight surface mesh. Now what I'm going to do is I'm actually going to poke a hole in it. I'm going to cut the thing in half. Okay, so why work on the whole thing if I'm just going to end up cutting it in half? Well, by meshing or by creating a model for the entire geometry, I know that there should be 0 lamina boundaries. If I had just created a model for half of it, there would be a collection of lamina boundaries at that symmetry because that's where there's a hole. Okay, and I don't know that if there may be other lamina boundaries in other places in the model, and because there are so many on that symmetry plane, it makes it hard to identify where others might be without exiting that panel. So that's why I did it for the whole car. Then I cut it in half because I only want to have to do half the work. I only want to create quilts for half of it. I only want to mesh half of it. And when I'm done, I can just mirror the result. Okay. So what I have here is I've colored each quilt independently. So each quilt has got its own color, and there are 850 different quilts. Again, these are logical meshing regions. Each one of these would get its own domain if I were to mesh this model. Again, you can use these to effectively define what your surface mesh topology is going to look like and represent physical things on the car, like the windshield, the hood of the car, you know, that kind of thing. So one of the things I'm going to do is I'm going to zoom into the door handle, and I'm going to focus on the door handle. So this door handle consists of 100 quilts, or a little more than 100 quilts. That's a lot of quilts to represent something this simple. And if I mesh it, I'm going to get a little more than 100 domains. And some of those domains are going to be very small. They're going to consist of very small triangles. adjacent to much larger triangles, driving up my area ratio and degrading the smoothness of my grid. So what I'd like to do is go through a quilting operation. Join these quilts into larger collections of quilts so that I get fewer domains. Again, I'm still resolving the exact same geometry. I'm just simplifying the complexity of that surface. So I'm going through and I'm assembling the individual quilts into larger collections. And I can always back up if I needed to. I can always break those things back up into their original quilt definition. Okay. All right, so I've assembled all of those quilts. Now I have 6. So I went from a little more than 100 quilts down to 6 quilts for that door handle. And you can see I get 6 unstructured domains that are still constrained to that geometry. All the elements are isotropic. It's nice and smooth. No large jumps in the area ratio or anything like that. Okay. Now I'm actually going through and doing this for the rest of the car. And I've sped this video up by about 5 times its normal speed. So it's going to be zipping through here, and effectively I'm doing the exact same thing. I'm just selecting quilts, I'm assembling them into larger collections, again to represent physical things on that car, and potential areas where I might apply boundary conditions in my solver or use for post-processing or things like that. So this is going to be one of the more time-consuming parts of the process. But again, once you do it, you don't have to do it again, and you can always back up and kind of start over. You can break these quilts back up into their original component quilts if you've joined too many of them together and that kind of thing. So I'm going through and joining all of those on the hood of the car. I'm taking this fillet that kind of wraps around the roof and I'm joining it together. And then what I'm going to do is I'm going to grab all of the quilts on the side panel of that car and join them together into a single quilt. Okay, so I've ended up with about 50 quilts. I've gone from 850 down to 50. Again, the same vehicle, the same geometry, just fewer quilts that I have to manage. All right, and now I'm going to create a uniform unstructured advancing front surface mesh on this car with a 1/2 inch grid resolution. I'm not using any curvature-based refinement constraints or anything like that. It's just a uniform surface mesh. You can turn those on. My process, I like to create a uniform surface mesh and then go in and refine after the fact. Maybe the point here to make is that you're never stuck. Okay, if you don't set up these constraints first, the curvature-based refinement first, you can always do it afterward. Okay, so that's why I feel like I have a little bit more flexibility if I create a uniform surface mesh and then go refine afterward, modify the attributes of my grid curves of my surface meshes afterward. So just to give you an idea, I'm going to refine the door handles. Those are a little bit too coarse, so I can grab those grid curves and I can change their average grid spacing from 1/2 inch to say 1/4 inch and redimension those grid curves. Okay, so you can see that it's propagated into the interior of that mesh. So again, you're never stuck when you've got your quilts and your models and you've created your surface mesh. You can always go back and modify attributes after the fact. Another thing I might want to do is turn on some curvature-based refinement. So I can grab some domains, I can jump into their attributes, and I can set like a maximum turning angle and refine. Something else that I can also do is I can decimate. So if I think this surface mesh is too fine in some areas, I can grab the domains, I can jump into the attributes, and I can say, all right, I want my max triangle edge length to be 1 inch rather than 1/2 inch. Okay, maybe I made it too fine. And I can go and I can decimate that grid. I can coarsen it. So after I go through and do that for the entire surface mesh, the next thing I want to do is I want to look at its quality. This is really important, particularly since we're doing shape deformation and optimization. So I examine that mesh, and the first thing I look at is the area ratio. In this case, the max area ratio is 16. And I can zoom to that and I can see where that problem is. That's a really high area ratio on the surface mesh. And it looks like there's a little connector that was created on the boundary of a quilt. And what I'd like to do is effectively merge those two nodes together and get rid of that connector, because that's resulting in some sliver triangles adjacent to much larger triangles, which drives up my area ratio. So I can just easily merge those two connectors together, and by merging those, the mesh is still constrained to the exact same geometry, but it eliminates those two sliver triangles, and my area ratio improves significantly. So I can grab that surface mesh and go look at the area ratio. In this case, it's 3.67. That's the max. It's less than 4. You want to try and keep your area ratio less than 4. That's an indicator of smoothness, how smooth your surface mesh is. The other metric I look at is the maximum included angle. In this case, it's 130. Keeping that less than 140 on the surface means we have nice, high-quality triangles. Okay, so area ratio and max included angle. Those are two prerequisites that I like to meet prior to creating my volume mesh. Okay, and then once I'm done with that, I can grab everything and I can just mirror the result and create the other half of the car if I wanted to do a full car analysis. Okay. In this short second video, what I'm showing is how you can add complexity. So that was just the body of the car with the fastback. No mirrors, nothing like that. Well, what if I wanted to add mirrors? Well, I can actually mesh them in another instance of Pointwise, so I don't have to add them to the model definition on the geometry level, and then import them. So I've basically appended that mirror grid into the project file that contains the body, and then I'm going to merge these two grids on the grid level itself, not on the geometry level, but on the grid level. So what I'm first going to do is I'm going to move that mirror, get it lined up with the edge of that window. And then what I'm going to do is merge them. So basically at their interface, they're going to be sharing some grid curves and some grid points. And I want to merge the two grid curves that are in the same location so that now they're sharing those entities, basically stitching these two grids together. And I'm merging the connectors now. Okay, so now they're stitched together. The last thing I need to do is poke a hole in that window domain for the mirror. So I'm going to just go and add remove edges, redefine that first edge, and save it. And now I've poked a hole in that window. So now that mirror is integrated on the grid level. This is a great way to add complexity. You can swap in and out components and only have to worry about them individually in their own instances of Pointwise and then bring them together after the fact. Okay. So the time required for this, if you look at this surface mesh, it's a little bit different. It's a little coarser than the one that we created in the video, but same concepts. The time required to clean this up, to mesh it, then create the volume mesh, conservatively is about 4 to 8 hours, depending on how much experience you have with the tool. Okay. So if you think about it, if we're going to be running an optimization and we're going to be creating hundreds, if not thousands of designs based off of this model, that is a very small price to pay for creating a very high quality mesh from the beginning. Okay, and that's the key, is we want to create something that is high quality so we can reuse it hundreds or thousands of times and not have to remesh for each new design iteration. Okay. So once we've created that surface mesh, the next step is T-Rex. We're going to create our viscous volume mesh using T-Rex, which stands for anisotropic tetrahedral extrusion. We've talked about this a lot. You advance off of the surface, you create these stacks of right-angled tetrahedra, which then you can combine to form unstructured hexahedra and prisms, and then tetrahedra in the far field region. It's controlled through 2 panels, so you can specify the number of layers, your growth rate, quality criteria, and your initial spacing in the boundary layer for that Y+ that you're looking to achieve. So in the end, for this model, the full model had 7 million elements, the full car. And we ran this using SimpleFOAM. We know that it's not exactly steady state, that wake is kind of whipping back and forth. However, it did converge to a quasi-steady state, and we averaged the drag over the last 1,000 iterations, and we were about 3% off the experimental coefficient of drag. So for this baseline mesh and this proof of concept study, we're on track. We were doing a pretty good job. Obviously, we would want to do a grid refinement study and look at a few more things, but for this proof of concept study, the first mesh that we created did a very good job, and it was a very high quality mesh as well. As you can see through this cut on the car as well as the cut on the mirror, you can see the prisms advancing out of those concave corners very nicely in this model. So speaking of grid quality, there are a couple of things that we can look at in the volume, on the volume level. One of the metrics that we like to look at for OpenFOAM particularly is the centroid skew. This is analogous to the non-orthogonality metric reported by OpenFOAM and CheckMesh. So we can set this to the maximum value that we're comfortable with, or OpenFOAM may be comfortable with, and see which elements violate that metric, and then go in and refine the surface or the volume in that particular area. Another reason we might want to do some refinement is to capture specific features and propagate them. So for example, the wake region behind the car, we can use a baffle which allows us to explicitly place points in the wake and propagate that wake downstream. So we've used baffles to provide refinement in that wake region. All right, when we're done, we then export to OpenFOAM. In Pointwise, we can set up all of the boundary conditions. We have all of the types available, the OpenFOAM specific types. We can specify those boundary conditions. We have patch, wall, symmetry plane, empty, wedge, cyclic, what have you. You can name them. All of that stuff gets exported to the boundary file and the polymesh directory. And if you want, you can set up sets and zones. We didn't need that for this particular case, but thought we would mention it because that is an option that's available. Okay, so at this point, I'm going to pass things over to Mark, and he's going to talk about how Sculptor was used to define these arbitrary shape deformation regions for this model. Mark?
Thank you, Travis. It's a pleasure to be here with you. Sculptor is all about morphing or shape deformation, and also using it in conjunction with optimization tools. It can do automatic shape optimization. Morphing with arbitrary shape deformation, which we call ASD, and shape optimization for fluid dynamics or structural mechanics in finite elements, or even both together in a MDO, multidisciplinary optimization work, such as fluid structure interaction. Another use of Sculptor's morphing is what we call shape matching, and this is relatively new, but a very growing and popular way to use Sculptor, and that is to be able to take a nominal shape or a given shape and morph it into a target shape. This is useful if you're wanting to look at as built versus as designed shapes. So once you already have a mesh, you can simply morph it into the actual shape and reanalyze it without having to go back to CAD and remesh. Sculptor can work with both internal and external CFD, structural mechanics, and also arbitrary shape of CAD itself. The image you see in the animation is a race car that Sculptor is morphing, and this is a real-time capture of the screen as the different shape change parameters that can be defined by the user are being changed so that we can see that in real time on the screen. Sculptor has this smooth volumetric shape change for practically any geometry, whether it's CFD, FEA, or even CAD. The user defines a set of control points and then groups some of the control points together in a way that will either rotate, scale, or translate the nodes in the model. This is done in a fashion so we do not have to go back to ReCAD and remesh. and it also maintains cell quality even for large deformations. We have found it's the small, subtle shape changes that can produce large improvements in your design, especially with CFD. And often the result is non-intuitive. Interfaced with most commercial and government formats, such as OpenFOAM, which we're working at today, but all of the popular commercial tools and government formats. We also, in finite elements, ANSYS, Abacus, Mastran, and so forth, they all can be imported and morphed and exported back into their same file structure. So we're not changing anything but the nodal location. So all of the cell connectivity, all of the boundary conditions, everything else remains the same. So you can take that directly back into the solver and look at the improvements for that. We do have a built-in optimization tool called Optimization Control Center. We have several gradient-based optimizers and also a design of experiments with a optimal lat and hypercube. We can also look at response surfaces and other graphics to help explore your design space. The optimizer we're looking at today with this DrivAer model is the design of experiments, and it's an interesting way to look at your design space. We also have batch mode so that Sculptor can be used with any other optimization software, and an API called Sculptor Server that you can actually incorporate Sculptor into your own software. Just a few of the example applications that Sculptor is used for by different areas in engineering, as well as many different companies. At aerospace, whether we're looking at the shapes of wings or fuselage or nacelles, as well as automotive and motorsports, such as you're looking at today with the DrivAer. Structural mechanics, if we want to mitigate vibration problems or look at fluid structure interaction or minimize stress, minimize weight, as well as internal flows, such as internal combustion engines and intake and exhaust manifolds. We also have customers using it for biomedical and other areas of research. For the problem that we're looking at for today, we have Sculptor as it's applied to this DrivAer. You see in the top image we have an ASD volume, which are control points that are like draped around the car in a conformal fashion to its shape, and these control points then can be grouped together to give individual shape change variables for an optimization, thus defining the design space that we're looking at. Sculptor has many useful features in the GUI to make this very easy, so it doesn't become tedious to be able to create the necessary control volume and grouping these control points together. The shape change parameters become the design variables that are based on the groups of ASD control points. And for this, I decided to look at 4 different shape change variables. One is taking the control points along the hood and the windshield interface there and moving them forward and backward so that there's one variable controlling the windshield rake. There's another set of control points for a rear spoiler height and extension. And then the fourth is the lower rear height or rake that controls the lower back end. The images on below just show that those have been moved, and it's a very smooth and volumetric deformation, so that the cell quality is maintained. Even the Y plus layers and the orthogonality on the boundary layer mesh. This next video that you'll see is a real-time capture of these 4 different variables being animated through 28 different design shapes. So we created a design of experiments with 28 distinct experiments or designs. And as you see, it changes all of these into these 28 different designs. So this populates our design space in 4 dimensions. And it creates these instantly, and then we can export all of these designs and send them to a solver, to the OpenFOAM solver, and that can be on your local machine, or they can be sent out to a cloud or some high-performance cluster, and then we get the information back from that. But before we look at the results of that design space, we look at the cell quality that was maintained, and this is a close-up view of the rear spoiler on this car, and we see the top is the undeformed shape, and even if we deform that a fairly large deformation of 15 centimeters downward, the cell quality is maintained. Not only the orthogonality of the boundary layer, the thickness of the boundary layer, so all of the differential deformation is out into the flow domain, where, and even out in there, it's smoothly spread out due to the ASD deformation, so that the resulting deformed shape has the same cell quality as the initial shape. Now, if we look at the plots of the solutions for those 28, and just to keep the plot here easy to see, we plotted the first 9 experiments, and we see in the red dotted line, that's the original, and the other 8 shapes are a subset of the 28 that we did look at. But we see clearly that even early on in the solution, and by the way, we to get a better solution than just using simple foam, we went to the pimple foam, or the transient solution. So even out to 0.1 seconds, we see that early on we can see that there is a definite difference and an improvement with experiment number 8 over the original shape. And this gives us about a 4.5% decrease in the drag as compared to the original shape. So clearly there's a sensitivity to the shape in the drag of this particular model. Now, if we look at this, the list of experiments, their shape change parameter values and the drag coefficient, we can see out of those 28 that we ran that 8 is clearly the best of those. Now, that might not be the absolute best that we could end up with, but it gives us an idea of the location in design space where our optimum can be found. If we don't have any more time to run some more experiments in that vicinity of experiment 8, then we can at least be confident that we have about a 4.5% decrease in drag. Other tools that Sculptor has, like we can take and look at the response surface, so we can create a response surface either with a kriging or a radial basis function, and be able to compare where we're at within design space and assimilate the information that we have even better, and then we can explore and look for other optimums that might be in that vicinity. So Sculptor has a lot of these tools that can quickly be used and to get a better idea what's going on in your particular design space with your shape change variables. It's easy to go back and change any of the variables, add more designs, without having to go back to CAD and remesh every time. So literally you could get hundreds or even thousands of different designs if you have that much time to calculate the CFD results for each one. We're more than happy to give you some more information. You'll have our contact information that you can contact us. I want to thank Travis and Pointwise again for this opportunity to work with them.
Thank you very much, Mark. So in conclusion, just to kind of recap through Pointwise and the meshing side, since we've kind of decoupled the optimization process and pulled CAD and meshing out, we found that solid modeling really allowed us to clean up that geometry and recover the original engineering intent using quilts. And then we were able to generate the very smooth, unstructured surface mesh that facilitated the generation of a very high quality volume mesh with T-Rex. And then in Sculptor, using arbitrary shape deformation, Mark showed how we can morph that final grid while maintaining very high cell quality and just eliminate the need to remesh after each deformation and automate that optimization process for possibly hundreds or thousands of designs, however many you have time for. Moving forward, looking at future work, some of the things that we want to do, look at more shape design variables at other locations on the car, things like the mirrors, the hood, or the underbody. And speaking of the underbody, this was the smooth underbody that we ran. So obviously one of the things we would like to do is add more detail and look at that detailed underbody for the DrivAer, and then perform a grid refinement study. Like I mentioned early on, this is kind of a proof of concept. We generated a baseline grid using our best practices, but because we have that clean analytic model in Pointwise, we can easily perform a grid refinement study on top of that model, and then potentially move from something like RANS to DES in the future. So thank you all very much for attending this webinar. A recording is going to be available by September 18th. That's this Friday. You can go to pointwise.com/webinar. And we're also going to include this mesh, the Pointwise project file for this mesh, on our website. So you'll be able to download that, export it to your solver, and run it as well. If you have any questions about Pointwise, please feel free to email me. And then, as Mark said, if you have any questions about Sculptor, please feel free to email him. And one last thing I did want to mention, today is September 15th. This is actually the 5-year anniversary of when we did our very first webinar. So I just want to say thank you all very much for joining us today, and thank you for those of you who have joined us in the past for all the previous webinars that we've done. We've really had a good time doing these, and we appreciate everybody who's participated and watched these webinars. So at this time, we're going to open it up for Q&A. So you can open up your questions dialog box and type your questions in, and Mark and I will answer those at this time. All right, so Mark, we've already got one question. One question is, how does Sculptor assure that the cell quality is maintained when morphing the mesh?
We have the option to actually calculate the cell quality during the morphing process, and it can report back to you what that is. But it helps to have a little experience with Sculptor so that you create the appropriate shape change variables and the adjacent control points so that you have enough room or volume to have a smooth deformation out into the flow domain.
Okay, if a large shape change is applied, I mean, is there a risk for poor quality elements to be created as part of that deformation?
Well, certainly you can do things that would make things unphysical, like turn things inside out and make negative cells. But you want to put some realistic controls on the range of the variables, the mins and the maxes of how far you can move these control points. It's like any tool. If you push it too far, it's going to, you know, it's not unlike CFD in and of itself. If you don't have a good mesh, if you don't have the right boundary conditions and so forth, you're not going to solve the real problem. So you just have to keep things within the bounds of good engineering, I would say.
Okay. Okay, so one question is, how did you refine the mesh on the bottom wall and all the way behind the car? Is it a separate domain face? Underneath the car, on the bottom wall, basically what I did is I created a separate domain that's just right underneath the car that is refined. And so I basically used the cell size that I had used on the lower surface of the vehicle, on the underbody, and that's the same cell size that I used for that domain right underneath the car in kind of its immediate vicinity. And then elsewhere, it kind of propagated out and increased in cell size. Now, and that was, like you said, a separate domain. Now, behind the vehicle, we actually stuck in an isotropic block, a TET block, with refined elements. And so we were able to add that as a face to our larger unstructured block so we could maintain that cell size downstream. Okay, do the viscous layers and volume mesh get recreated automatically, or do they need to be done manually? I'm assuming maybe recombined. The viscous layers on export will get combined into, if you're growing off of quads, they'll get combined into unstructured hexahedra wherever possible. And if you're growing off of, you're using T-Rex to grow off of triangles, they'll get combined into prism elements. And elsewhere are going to be tetrahedra or pyramids to help transition from quad faces to the tetrahedra, and that's all done on export. What is the quality of the cells where the tires touch the floor? That's a great question. Actually, the quality is not that bad there. So there's a couple different ways to handle that, and we've seen a couple of different ways. One is you can clip the bottom of the tire, which is what we did in this case. We actually just clipped the very bottom of the tire. You can actually put a pillar, so a very small kind of cylinder underneath the tire that attaches to the ground plane. We didn't do that in this particular case. That case obviously results in the best quality. And what you would do is you would refine in that region, so you would get some very high quality elements in there. The way that we did it by clipping, you do get a very small angle. But for this case, our Y plus was about 50 to 60. So our initial spacing was, I mean, I wouldn't say rather large, but it was larger than if we were using a Y plus of 1, let's say. So the quality of the cells in that region, it didn't violate the metric that we were looking at. Okay, we were looking at the centroid skew, setting it to like a value of 0.7 or something like that, and it didn't violate that metric. So far, really good questions. Any other questions? Still quite a few people online. Are you going to do the Tuesday on appending and merging meshes? I'm assuming maybe you mean tutorial Tuesday on appending and merging meshes. That's not a bad idea, actually. Quite possibly. We'll jot that one down and think about doing that. Those videos are less than 3 minutes long, so we'll have to tighten it up a little bit. But great idea. Okay, any other questions? Leave it open for another couple of minutes. Sure, some questions will come streaming in. How much time does it take per run in Sculptor? Mark, you recall how long it took?
Well, once you have the ASD set up and the groups defined, it actually takes a matter of seconds, less than a minute, to have it create. In this case, it created those 28. It could have created 100 or even 1,000 different designs and help to create the design of experiments that you need. But to export those, it just isn't. The only time that it really takes is just writing out all of those different experiments to files, and then you can take those. But as soon as those are created and they're sent to OpenFOAM, each one of those would take an OpenFOAM solution. So, but if you started with your initial solution and restarted from that, since all we're changing is the node locations, all of the cells can be, preconditioned with the previous solution. So it may only take 10 or 20% of a solution as compared to solving it from scratch.
Mm-hmm.
So those subsequent calls after your initial one is already made, it's very efficient to use optimization to run OpenFOAM or any other CFD tool for that matter that can be restarted from an initial data set.
Mm-hmm. Okay. Once a surface mesh is modified with Sculptor, do the viscous layers and volume mesh get recreated automatically, or do they need to be recreated manually? This is kind of I think both of us could tackle this. This doesn't require remeshing, right, Mark? I mean, we're meshing, we're morphing this mesh and just modifying the point locations and then dumping that data out. There's no recreation or regeneration of that mesh. You want to say a couple things about that?
Yes, and because the Sculptor is morphing things volumetrically through what we call the trivariate nerve, that parametric, the movement of all of those nodes with respect to each other is very smooth, so that we maintain the cell quality, we maintain the boundary layer thickness, we maintain the orthogonality, and we also maintain cell quality out into the flow domain, so that there's no need to remesh, there's no need to smooth. It all happens during the deformation.
Right, and the changes, the actual deformation itself and the effect on the nodes in the mesh is rather isolated, is it not?
Yes, it's a local. You have local control. So if we're moving a control point near the rear of the car, up to 2 control points away from it in any direction is not moved at all. Mm-hmm. It's all very local.
Right.
And so we can focus and create the desired design change intent very accurately, and just by placing the control points where we want them, and then including the right control points in the shape change variable.
Right, and the benefit there is that because we're using the same mesh and these changes are kind of done locally, we're we're not really concerned anymore that the mesh is going to be influencing the solution in the way it would have had we had to remesh the entire thing from scratch. Because if we had to remesh it from scratch, now we're introducing an entirely new mesh to the solver, and we're not quite sure now if the changes are coming from that or if they're actually coming from the parametric changes suggested by the optimizer. In this case, because we're deforming the exact same mesh and changes are done locally, it's kind of a best case scenario.
There's one other aspect of this is that you may, if you have any questions about these, send us a model, send us a grid, and we can make some deformations on it, send it back to you, and you can interrogate, investigate cell quality and the solution to it. It only takes us a few minutes to do that. We'd be happy to show you that if you'd like.
One question was if this was RANS or LES. This was a RANS calculation. And then another question was maybe you could reiterate what the 4 control parameters were for this optimization.
Well, we grouped the control points near the windshield so that we controlled the rake or the angle of the windshield with respect to where it meets the hood. We also grouped the control points at the rear so that they could move vertically to raise and lower the spoiler, as well as moving it forward and aft. And then we had the 4th set of control points underneath the rear of the car so that it controlled the rake from the wheels to the bottom of the trunk area. Mm-hmm. We could have looked at some fine deformation of the spoiler itself. That's what we do when we're looking at the race cars, whether it's Formula One or the Sprint Series and other Le Mans Series race cars that we have helped different teams work on. We can actually morph the shape of the fin or the spoiler itself, or the shape of the splitter on the front of the car. Just depends on what you're trying to do and what you're trying to control. Hmm.
Okay, any questions before we close up? Wait just a minute. Okay. All right. Then with that, we'll end this webinar. Thank you again, everybody, for attending, and thank you all for sticking around for the Q&A session. And we look forward to seeing you all in the next one. Bye.